In this video, we will be discussing about A-star algorithm. We will apply the A-star algorithm to a graph and find out the shortest path from a starting node to a goal node. So A-star algorithm contains three functions mainly. One is F, the G, which is the cost incurred from the starting node to the current node, and you have H or H bar, which is the estimate of the cost incurred from the current node to the final node. And then we have F bar, which is also an estimate, which is a combination of G and H bar. So we will be using these three functions to compute the cost at each node, and finally we try to choose the shortest path from starting node to the goal node. So let us see how we can find the shortest path for this particular graph. So as you can see here, we have a starting node. The starting node is 0, 0. So let me write it here. So start node is 0, 0, and the goal node is 1, 1. So there are multiple paths to reach goal node from the starting node. So the cost incurred here is 5. The cost incurred here is also 5. This route 0, 0, 1, 0 and 1, 1 is 5. 0, 0, 1, 0, 1 and 1, 1 is also 5. The cost incurred through the final route 0, 0, 1, 0, 1, 2 and 1, 1 is 3. So we are able to see here, since the graph is short and we were able to do it, but we want a program or an algorithm to do the same task and find out and give us this shortest path. So I have the code here, Python code for A-star algorithm. I'll be discussing this Python code and I'll be explaining how this Python code works. So this A-star algorithm relies on these three functions, G, H bar and F bar. Once again, G is the cost incurred from the starting node to the current node. So there are three nodes. One is starting node, current node and the goal node. So the cost incurred from the starting node to the current node is given by G. The cost incurred from current node to the goal node is given by H bar, and the combination is given by the F bar. So, and we also have open list and closed list. So this open list contains the list of nodes which are supposed to be pursued. Closed list contains list which have already been pursued. Mostly we will be using open list. So in the beginning, the open list contains only one node, which is the 0, 0, and it also contains some starting score for F, which is initialized as 0, 0, 0. This is the starting node, which is 0, 0, and this is the cost incurred in the beginning, which is initialized as 0. That can be seen here. Open list is 0, start. So here the start is 0, 0. So let me first explain how the graph is constructed, how the graph is represented, and then we can go to the A-star algorithm. So this is the graph. The graph which is given here is represented in the form of a dictionary. It's a nested dictionary. So as you can see here, 0, 0 is the key, and this key has a value. The value is a dictionary. So this value is also a dictionary. So 0, 0 has two neighbors, 0, 1 and 1, 0. And the cost incurred to reach 0, 1 is 3. The cost incurred to reach 1, 0 is 1. And this, both the cost and the nodes are represented using a dictionary. So cost incurred to reach 0, 1 is 3, and the cost incurred to reach 1, 0 is 1. So this whole thing is represented as the neighbors are represented in a dictionary, and this whole dictionary is the value for the key 0, 0. In the same way, we can write for all other values 0, 1 as one node, and it has neighbors as 1, 1 and 0, 0. You can represent the same in the form the value as a dictionary. So the whole graph is represented as a nested dictionary. and our start node is 0 comma 0 and our goal node is 1 comma 1. We are supposed to find the shortest path, and we are invoking this function a star. We are giving this graph as an input, starting node as an input, and the goal node as an input. So let us see how this function works and how we are able to get the shortest path. You can see here already the shortest path we have already seen. So this is for a different case. So let me just quickly run this and show what would be the result for this particular case. So as you can see, the shortest path is 0 comma 0, 1 comma 0, 1 comma 2, and 1 comma 1. So this algorithm is giving us the right shortest path for this particular graph. So let's find out how this algorithm is working and how we are able to get this shortest path. So as I've said, a star is the function which we are going to write, and we are giving graph, starting node, and the goal node as the arguments. So let's see how this function works. So a star takes the graph, whatever we have constructed, and the starting node is 0 comma 0 and the goal node is 1 comma 1. In the beginning, as I've said, there will be an open list which contains all the nodes which are supposed to be pursued, but it also has 0 as the f score. So we will be saving all the nodes with their f scores in this open list. In fact, we are not saving by any queue or stack, but we'll be following something called as a priority queue. So we use heaps to push and pop the nodes from this list. So why we are using heap? Because we want to implement the priority queues, and here we want to implement min heap, because we want to extract the node which has the minimum cost from this list. So this open list will keep on contain different nodes with their f scores, and we would like to always pop the node which has the minimum f score. So rather than first in first out or last in first out, we are following a priority queue which is based upon the one which has the minimum score. So currently there is only one node which has a score of 0. So this is the node which we are going to pop, and let's see how it goes. In the beginning, the G scores are all infinite. So let me write it here. So G scores. So I'll be using a different color for G scores. So I will be writing G scores here. So in the beginning, G scores, I'll save it in this form. Just for the notation, I'm using this convention. So first node is 0 comma 0. So what we are doing here, the G underscore score in the beginning, for every node we are initializing it as infinite. So as you can see here, INF, which is infinite. So we are taking every node from this graph and we are initializing, or we are assigning the value infinite. So let me write that. So in the beginning, 0 comma 0 is infinite, 0 comma 1 is infinite, 1 comma 0 is infinite, 1 comma 1 is infinite, and 1 comma 2 is also infinite. So these are the keys and these are the values. So let us see how these values get updated as we move along. Also, the f scores are also infinite. So let me use a different color for that, f scores. So f underscore score. So these will have values in the beginning. For every node, f scores are also infinite. So 0 comma 1 as infinite, 1 comma 0 as infinite, 1 comma 1 as infinite, 1 comma 2 as infinite. So this is also a dictionary, and we will be updating this dictionary and assign the values as we move along. So we have initialized G score and the F score, and we have something called as heuristic function. As I've said earlier, H bar is the cost incurred from the current node to the goal node, and that is computed using a heuristic function. And here we will be using a heuristic function called as Manhattan distance. So let me write the function for Manhattan distance. So I'll shortly call Manhattan distance as MD. So let me use this here. So Manhattan distance. So if you have two coordinates, x1 comma y1 and x2 comma y2, you can compute the Manhattan distance MD as absolute of x2 minus x1 or x1 minus x2 is, since it is absolute, plus y1 minus y2. So this is what is the Manhattan distance, and we compute h bar, which is the heuristic function, by using this Manhattan distance. So now let us see how things will get updated. And we have also one more list or dictionary which is called as came from. This is needed because we need to note down from, so that note down the path, so that towards the end we will be able to trace back from which path we came from. So came underscore from, in the beginning it is an empty dictionary, but we will have later values here also. So let me keep that empty. So now, so there are two loops, one is while loop and the other is for loop. So while loop is looking for all the nodes in the open list, and for loop is looking for all the neighbors for the particular node which we are working on. So let's take the first element from the open list. So if you see, the open list as of now contains only 0 comma 0 comma 0. So contains only one element, so I think I might need space here, so I'll keep this in some other place. So let me just scroll down and I'll write came underscore from here. Came underscore from, it is also a dictionary. I'll write it here. This space I'll use it for open list. So in the very beginning, so what we are doing is we are popping the first element from the open list. We know the open list contains 0 comma 0 comma 0. So as you can see here, this is a list, but it contains tuples inside it. So this is a tuple. This is a tuple, and this is also a tuple. So nested tuple and inside a list. So we would be using this as the first node, because that's the only node which we have, and that we will be considering as the current node. So our current node is 0 comma 0. So let me write it here shortly. Our current node, let me just keep this separately. So current node currently is 0 comma 0. This will be keep on using it. Okay, so now we have popped that, and current node is 0 comma 0. That is not the goal node, so it will go and check for its neighbors. As you know, 0 comma 0 has a different set of neighbors. We have 0 comma 1 and 1 comma 0, and we will be working on each of those neighbors. So let's take the first neighbor, which is 0 comma 1. So your neighbor would be 0 comma 1, and we will be computing tentative underscore g underscore score, which is the g underscore score of current node. Current node is 0 comma 0. the g underscore score of current node is infinite, and so as you have to see, g underscore score of start node, we initialize it to 0 and not the infinite. So all other nodes, it has been initialized as infinite, but for the starting node, which is 0 comma 0, it has been initialized as 0. So let me just erase this and keep it as 0. So this is 0. So now our tentative underscore g underscore score will be g underscore score of current. Current is the 0 comma 0 node, and the g underscore score of current node is 0. So this would be 0. And the graph of current, the graph of current is, so 0 comma 0's current neighbors are 0 comma 1, and this is to access the dictionary values. So the graph underscore current will access, because since it's a nested dictionary, we have two square brackets here. So what we are going to get here is graph of current of neighbor. This graph of current is this 0 comma 1 and 1 comma 0 with their corresponding weights. But graph of current of neighbor, neighbor is currently we are working on 0 comma 1. So its value is what we are going to get. So it would be 3. So g score current is 0 plus this is 3. So which would be tentative g score is 3. So let me write that also here just for notational purpose. So tentative g score value is currently 0 plus 3, which is 3. So now we will be seeing tentative g score, is it less than g score of neighbor? What is the g score of neighbor? Neighbor is 0 comma 1. G score of neighbor is infinite, but the tentative g score is lesser than the neighbor. So it is satisfying this condition. So it goes inside and it saves km underscore from of neighbor to current. So let's now go down and replace, keep it here that km underscore neighbor should contain, so current. So what we will be doing, we know that it is also a dictionary. So we will be writing neighbor is 0 comma 1 and it came from 0 comma 0. This is what we are going to write. So now we have written km underscore from the g score of neighbor. So g score of 0 comma 1 is going to be replaced with tentative g score. So this was infinite. Now this would be replaced to 3. So let us erase this. So tentative g score is 3. So now this is 3. So your f underscore score of neighbor will be tentative g score, which is 3, plus heuristic of neighbor comma goal. So heuristic of neighbor comma goal. So if you see, current neighbor is 0 comma 1, which we are working on, and the goal is 1 comma 1. So if you compute the Manhattan distance between 0 comma 1 and 1 comma 1, so apply this formula. 0 minus 1 is 1, abs is 1, so 1 minus 1 is 0. So Manhattan distance is 1. So this heuristic of neighbor comma goal would be 1. So tentative underscore g underscore score is 3 and this heuristic is 1. So our f score would be 3 plus 1, which is 4. So let me just remove the f score of neighbor from infinite to, so this would be 3 plus 1, which is equal to 4. So 3 is coming from tentative score and 1 is coming from the heuristic function. So that would be 3 plus 1 is 4. So now our heap push. So we are going to push the current f score, which is of the neighbor, which is 0 comma 1, into the open list with its f score. So current f score is 4. So let me just represent in our so let me just write. So this is done. So next one is, within the open list we will be having 0 comma 1 as, so the cost is the cost we have to write first. The cost is 4 and the node is 0 comma 1. So this will be going to the open list. So now open list contains 2. Okay, 4 comma 0 comma 1. So now once we have pushed, so we have completed one neighbor. So one neighbor of 0 comma 0, which is 0 comma 1, has been completed. The next neighbor is 1 comma 0. So let us do the same thing for 1 comma 0. So if you do the same thing, so our tentative G score would be G score of current. Our G score of current, our current node is still 0 comma 0, and G score corresponding to that is 0, and G graph of current of neighbor, which is 1 comma 0, and its corresponding weight is 1. So what we will be getting, the tentative G score is 0 plus 1, which is 1. So let us replace 0 plus 1, it is equal to 1. And now our tentative G score is 1. Now K, so if tentative G score is less than G score of neighbor, G score of neighbor is G score of 1 comma 0, which is infinite. Tentative G score is lesser, so replace that with 1. Okay, so this is done. So it is satisfying, it comes inside. So Km underscore from of neighbor would be equal to current. So if you go here, so we have to replace here, we have to keep our Km. So we came to 1 comma 0 from 0 comma 0. So this we have to remember. Okay, so then we will be looking for G score of neighbor, G score of 1 comma 0, which is tentative G score. So G score of 1 comma 0, we have replaced it with tentative G score, which is 1. We have already done this, we have raised it and done it. Okay, and F score of neighbor is tentative G score, which is 1, plus heuristic neighbor. So heuristic function, Manhattan distance, we have to apply between 1 comma 0 and 1 comma 1. So that would be 1 minus 1 0, 0 minus 1 1. So apps, so 1 value. So you will have Manhattan distance as 1. So that would be tentative G score is 1 and Manhattan distance is also 1, which would be equal to 2. So this would be replaced with, so if you see, the F score value would be replaced with 1 plus 1, which is equal to 2. So 1 comma 0 as F score of 2. So this would be pushed to the heap once again. So if you push this to heap, so let's remove this. So now you will have a new value, which is 2 comma, what is the node? 1 comma 0. So this is also now introduced into the open list. So we have pursued completely 0 comma 0 with 2 neighbors. So both this for loop is done. Now we will be coming back and checking to see if there is anything to be popped from the open list. Since it is a priority queue, since this open list, since we are popping using priority queue, so and we are following min heap, so always the minimum value would be popped out. So this would be popped out. So let me just rearrange the things. So after you have this, so when you do the min heap, this will come here and this will go here. So let me just make the changes. So 4 will come here, which is for 0 comma 1, and 2, which comes here, which is 1 comma 0. So this replacement we are doing because this list is going to be min heaped. When you do min heap, the one which has the lowest one will come to the top. So this is already done, this is completed, we have eliminated. So the next one is 2 comma 1 comma 0. So that will become the current node. So 2 of 1 comma 0 will become the current node. So let me replace now the current node with 1 comma 0. So So now we have the open list and the current node is 1 comma 0. Let's find the neighbors for 1 comma 0. We have 3 neighbors, 1 comma 2, 1 comma 1 and 0 comma 0. So let's do the same operations once again and find out how this goes on. So let's go a little more quickly. So current node is not goal node. So neighbors of 1 comma 0, which is 0 comma 0. So if you take the 0 comma 0, although it is coming back, but we will see why it will not choose the path of 0 comma 0. So your current node is 1 comma 0. So G score of 1 comma 0 is 1, and graph of current node of neighbor 1 comma 0, the current node is 0, the neighbor is 0 comma 0. So that value is 1. So this is 1 and this is 1. So tentative G score would be 2, and tentative G score is 2, and the G score of neighbor is neighbor here is 0 comma 0, which is G score is 0. So 2 is not less than 0. Our tentative zeros, so let me write it here. Our tentative G score at this moment is G score of current. Current is this 1 comma 0, which is 1 plus, and graph of current of neighbor, which would be the path distance 1. So that would be 1. So this will come to 2. But this 2 is not less than G score of neighbor. Neighbor we are looking for 0 comma 0, which value is 0. So 2 is not less than 0. So it will not pursue this path, which means it will not come back. So it will pursue the other neighbors. So 1 comma 0 has 1 comma 1. So let us see what happens if it pursues 1 comma 1. So your neighbor is 1 comma 1. So G score of current is once again 1 comma 0 is 1. Okay, and graph of current of neighbor, this graph of current of neighbor will be 4. So this would be 4, and what you get is tentative G score as 5. So now tentative G score is 5. G score of neighbor is 1 comma 1, and its G score is infinite. So 5 is less than infinite, therefore it passes. So it comes inside km underscore from of neighbor. So neighbor is 1 comma 1. So that would be saved into the km underscore from dictionary. So let us save that. So your km underscore from contains 1 comma 1 with came from 1 comma 0. Okay, now we have saved that. So let us now go back, and so we have G score of neighbor is 1 comma 1. So G score of neighbor should be tentative G score, which is 5. Earlier it is infinity, now this has to be replaced with 5. So let me replace that. So this will be 5. So also F score of neighbor, which is tentative G score, which is 5, plus heuristic of neighbor and goal. So neighbor and goal here are same, 1 comma 1, and goal is also 1 comma 1. So this is 0. So 5 plus 0 is 5. So here I'll be having this value as 5. 5 plus 0, that is equal to 5. So now I got F score of a new F score, which is 5. So I need to keep push into it. So let me push that. So when I push this, my value is 5 F score, and the corresponding neighbor node is 1 comma 1. But still it is having a larger value. So even if you do min heap, there will not be any changes. The list would be same. So we have completed the second neighbor for 1 comma 0. So we have the third neighbor, which is 1 comma 2. So let us do the same thing. So if you do the same thing for 1 comma 2 as the neighbor, so your G score of current is the 1 comma 0. 1 comma 0's G score is 1, and graph of current of neighbor, which is this value 1. So your tentative G score would be 1 plus 1. So that would become 2. So let's change it. So that would be 2. So your tentative G score is 2, which is less than G score of neighbor. G score of neighbor is G score of 1 comma 2 which is infinite. So 2 is less than infinite, it is satisfying. So it goes inside and replaces km underscore from to the current node. So come down and keep it here where you are coming from. So I came to 1 comma 2 from 1 comma 0. Okay, so let's go back and see now the G score of neighbor should be, the neighbor here is 1 comma 2. So G score of neighbor currently it is infinite. Now that has to be replaced by tentative G score, which would be 2. So, and the F score of neighbor should also be replaced with tentative G score, which is 2, and heuristic. So if you compute the heuristic function, 1 minus 1 is 0, 2 minus 1 is 1. So 1. So tentative G score is 2. So this will be replaced by, so let me also erase this. So you have tentative G score is 2 plus your heuristic function has cost of 1, which is equal to 3. So yeah, so now the F score, you have a new value. So let me just edit this, and you will have a new element into this list, so that which has a F score of 3 and value as 1 comma 2. So in this way our open list has changed, but now you can see here this is having a minimum value, so things will change here. So this will come here and everything will get adjusted. Okay, so I'm just notating this here. So 3 comma 1 would come here, because when you do min heap it will come here. Okay, so now we have completed 1 comma 2. So we have pushed, and this both the neighbors for 1 comma 0, all the neighbors are done. 0 comma 0, 1 comma 1, 1 comma 2, all are pursued. Now we are completed this for loops. It will go back to the open list and try to pop the next one. So we have popped this one. Now the next best one is 3 comma 1 comma 2, not 4 or 5. So this is having the minimum F score. So it will pop this. So your current node will become 1 comma 2, and let's see what happens now. So when the current node, so let me change here, your current node is now 1 comma 2. Okay, just to make it more neat, I will write this here instead of having in this form. So let me just write it here, 4 comma 0 comma 1, and let me erase this 3 of 1 comma 2. So 3 comma 1 comma 2, 5 comma 1 comma 1, this would be 4 comma 0 comma 1. Comma 0 comma 1. So now we are going to pursue this as the current node 1 comma 2, and let's see what happens. So 1 comma 2 has both these nodes 1 comma 0 and 1 comma 1. Once again it violates 1 comma 0. I'll just quickly show why it will not consider. So if you consider neighbor node as 1 comma 0, so the current G score value, G score of current, which is G score of current is 1 comma 2, and it's 2 plus graph of current of neighbor, which is 1 comma 0 1. So 2 plus 1 is 3. So your tentative score becomes 3. So let me write it here. So 2 plus 1, which would be 3. So your tentative G score 3 is less than G score of neighbor. G score of neighbor is, your neighbor is 1 comma 0. So G score of neighbor is 1. So 3 is not less than 1. So it violates. So it will not pursue this path. So the next leftover is 1 comma 1. So your neighbor node is 1 comma 1 and your current node is 1 comma 2. So let us see what happens. So when you compute, so this has violated, so all these things has not been executed. So it comes to the next iteration of the for loop and checks for tentative, computes the tentative G score. So tentative G score So current node is 1 comma 2, neighbor node is 1 comma 1. So G score of 1 comma 2 is 2, and graph of current of 1 comma 1 is 1. So that would be 2 plus 1, that's once again 3. So tentative G score is 3. So this tentative G score 3 is less than G score of neighbor. G score of neighbor, which is 1 comma 1, is 5. So this path has resulted in 5. That was the best previously. Now that is being replaced. So now what is happening is the tentative G score is 3 and the heuristic, so we are trying to replace, so G score of neighbor, G score of 1 comma 1 is what we are going to replace. That will be equal to tentative G score, which is 3. So earlier it was 5, now that is being replaced to 3. So let's do that. So this step, tentative G score of neighbor is 1 comma 1. So for 1 comma 2 is the current node and 1 comma 1 is the neighbor. So G score of 1 comma 1 is the tentative G score, which we computed already, which is 3. So now F score of neighbor, which is F score of 1 comma 1, earlier it was 5 plus 0, now that would be replaced by, so F score of neighbor will be replaced by tentative G score, which is 3 plus your heuristic function. So neighbor and the goal are same, 1 comma 1 and 1 comma 1, so it would be 0, so the cost would be 3. So this is the cost which would be once again pushed into the open list. So our open list now will contain one more, which is 3 comma 1 comma 1 comma 1. So once again, this is better than these two. So this will go here. So I'll write it directly here. So 3 comma 1 comma 1. Okay, and you can close it, close the list here. Yeah. So is 3 comma 1 comma 1. So this is done. Once it is done, we are going to the next current node is this, but the current node is same as the goal node. 1 comma 1 is same as the goal node. So if that is the case, you will be directly calling the reconstruct underscore path. You will not be anymore pursuing this. So reconstruct underscore path is a different function. So let us see what happens. So we'll be tracing back the actual path. That's where this km underscore from will help us. So km underscore from is the input for it, and current. The current is 1 comma 1. So okay, I think we haven't actually yeah, I think it's fine. So our current node is 1 comma 1, so that is the first one. So we are looking for the value current in km underscore from. Km underscore from is a dictionary. So I'm taking, so the current which is 1 comma 1, is it in km underscore from? Yes, it is in the km underscore from. So that becomes current is equal to km underscore from of current. So 1 comma 1 is the key. It came from 1 comma 0. So that is what we have written, but I think we have missed out one more step here when we have so 1 comma 1 came from 1 comma 2, so that we haven't updated here. So that step we have missed out earlier, so that's why we are not able to see here. So 1 comma 2, so when we have run the neighboring node, so this step, so when we have been running this step, when we have updated the G score of neighbor, which is 1 comma 1, before that we are supposed to change this km underscore from of neighbor, which is 1 comma 1, is 1 comma 2. So that will replace 1 comma 1 by 1 comma 2. That step we have missed it earlier. So that will get updated. So now when you are finally going to this reconstruct underscore path, so you will reach here and you will see your km underscore from is this dictionary, and your current node is 1 comma 1. So currently the current is 1 comma 1, the path contains only that one node. So 1 comma 1 is there in the km underscore from, and your current will now get updated to the value of 1 comma 1. So km underscore from of 1 comma 1, which is 1 comma 2. So your current node is now 1 comma 2. So from here we came to here 1 comma 2. So that would be appended in the path. So your path variable, earlier it was only 1 comma 1. Now the path will update the current node. What was the current node? From 1 comma 1 we came to 1 comma 2. So km underscore from of current, this is a dictionary, this is a key, and this is the value corresponding to it. 1 comma 2 is the value. So that becomes the current, and that current has to be appended in the path. So that is 1 comma 2. And once again you learn it. So you will take 1 comma 2, current is 1 comma 2. So it is there in the km underscore from. Now current will be get updated to the value of 1 comma 2, which is 1 comma 0. So now current is 1 comma 0, and that would be appended into the path 1 comma 0. Once again 1 comma 0 is there in km underscore from, because this is a key, and its corresponding value is 0 comma 0. Now current becomes 0 comma 0. So in this way we will be tracing back. So 0 comma 0 is also there here, but 0 comma 0 is not the key here. So this while loop ends, and we have to reverse this path, and this would be the actual path. So 0 comma 0, 1 comma 0, 1 comma 2, 1 comma 1 is the solution. And from here to here you have 1, from here to here you have 1, and here to here you have 1. So total cost is 3. So that's how we will find the shortest path using the A-star algorithm for graphs.